Okay, today we're going to be watching a video on dynamic equilibrium. That was yesterday's topic. It's a 10-minute video. It's available on Safari Montage within the school. And that's about it. That's about the description for that. Today, after you guys have taken your notes on 17.1 and 17.2, specifically 17.2, we're going to talk about this idea about writing an equilibrium constants. And we've got worksheets to complete here. Tonight's worksheet is entitled, what is the title? It is titled KEQ problems. I'm assigning the sorry, gotta get my pen here. Gotta make it the pens. I'm assigning the evens tonight because those are the problems that if you can do those problems, you can do the odds. I'm going to come up with my worksheet answer key is going to have both the evens and the odds. So you can, if you don't do so hot on the evens, try out the odds and see how you did. Okay. You take a look here. This is a beautiful, beautiful cave. What you do see are stalactites and stalagmites. Tights are tight. They hang from the top. Stalactites have a T in them. They look kind of like a T. And stalagmites, well, you can see they look kind of like an M. These stalactites and stalagmites are kind of the focus of why equilibrium is important today. I told students today that the actual reaction I'm showing isn't important, but the general idea of what's going on is. Okay, here's the basic idea. Let me get my pen here. Okay. This here is the chemical reaction that represents what happens when a stalactites or stalagmites are formed. Stalactites and stalagmites are made up of calcium carbonate. This is also the limestone bedrock that is above the cave. Above the cave, you've got limestone, Limestone, and above that, you've got soil, and then you've got, the earth, and here we have some rain falling down, some precipitation coming down, all right? The big idea is this. This chemical reaction drives making stalactites and stalagmites over thousands and hundreds of thousands of years. The idea is this. This is the limestone calcium carbonate. This is the component of acid rain, the hydronium ion. The hydronium ion falls into the soil. It goes through the soil and hits the limestone where the hydronium ion is acidic, and it dissolves calcium carbonate, the limestone. This solution continues to seep through until it reaches the cave, the top of the cave up here, where something interesting is going on. All right, so water through the limestone, it dissolves the calcium carbonate. And when it dissolves the calcium carbonate, it dissolves it into the calcium ion and the carbon dioxide and water. Okay, so we have this solution here. This solution is what's seeping down into the cave. Okay, now in the cave, there's less CO2 inside of the cave, and that pulls this CO2 here out of the droplet of solution. This drives the reaction backward, which forces calcium carbonate to be made. And that calcium carbonate is deposited into these limestone, that is what's called a stalactite or a stalagmite. This reaction obviously relies a lot on concentrations, specifically the concentration of carbon dioxide. The whole reason why stalactites and stalagmites are so beautiful and so smooth is because they're made by drops of water, drops of solution, one calcium carbonate molecule at a time. So one molecule gets deposited every time a molecule of carbon dioxide gets outgassed out of the solution. It's a very slow, tedious process. Now, in case you didn't notice it, this guy here, that's a person. These are some among the largest caves in the world. They're located in the Persian Gulf. These caves probably took hundreds of thousands of years for these stalactites and stalagmites to form. And as you can see here, this is what happens when a stalactite and a stalagmite connect to each other. You get a column. And I think that's a beautiful, beautiful structure. All right. At any rate, I diverge a little bit. What does this have to do with the constant of equilibrium or an equilibrium constant? Well, the mathematical relationship for a KEQ, equilibrium constant is KEQ, relies on the product and the reactant concentrations, just like the concentrations of carbon dioxide that we were talking about in that chemical equation just a moment ago on the last slide. All right. In this case, we write out that the KEQ is dependent on the concentration of the calcium ion times the concentration of the carbon dioxide ion, all over the concentration of the hydronium ion squared. Now, if you're looking for the reaction, here it is. This is the reaction again. You can see here's the calcium ion written on top. Here's the carbon dioxide molecule written up here, and the hydronium ion written down here. If you take a close look at this, one of the things that you notice is this is a heterogeneous reaction. It's one where heterogeneous, meaning that we have multiple states of matter going on here. We got solids, we got aqueous, we got liquids. In a heterogeneous reaction, according to Dr. Zumdahl, the author of the book, the textbook, we do not include solids or liquids. There's a good reason for this. These things are concentrations. That's what the square bracket stands for, is concentration. So this is a molarity of calcium ion. This is a molarity of carbon dioxide that's dissolved in the water. This is a molarity of the hydronium ion that's been dissolved. All of these are molarities. How do you get the molarity of a solid? Molarity is number of moles per liter. There is no solution to have a number of liters of. So there is no molarity by definition for calcium carbonate. So we can't include it in here because there is no molarity. Same thing for pure liquids. Pure water, there's nothing that's dissolved in. So there isn't a solution to say number of moles per liter of solution. So we can't do that either. The water is what's making up the solution. So the rest of this stuff can be included in the KEQ. Now, why are we studying KEQs? Well, KEQs tell us what's going on in a chemical reaction. If I actually allowed this chemical reaction to occur, to go to equilibrium, and measure the calcium ion concentration, the carbon dioxide concentration, and the hydronium ion concentration, we could solve this. And these values of KEQs are available. You can look them up online or in books. The KEQ equals 1.4 times 10 to the negative ninth at 25 degrees Celsius. This part, it's important, but we don't so much care about it. The at 25 degrees Celsius is there because this reaction can occur at different temperatures. If you understood what was going on when you read 17.2, you realize that different temperatures mean different KEQ values. So if we raise the temperature, that's going to push the KEQ value to a different value. But the value of the KEQ is what we're really looking at here. 1.4 times 10 to the negative ninth is a really small number. It's like 1 billionth, 14 billionths of is what the number's value is. 14 billionths. That's incredibly small. Let's do it this way here. Sorry. Let's talk about it in these terms. If our KEQ is a function of the product over the reactants, the concentration of the products over the concentration of the reactants, at its most basic level, if I want to get a large KEQ, the way I do that is I have a large number of products over a very small number of reactants. Okay, this sort of a KEQ, a large KEQ, which that reaction wasn't, would favor, we say that it favors products. Okay, because there's a lot of products. It's just a simple ratio. A large number over a small number gives you a large number. Now, if I want a KEQ that's small, that would be done by taking a small number and putting over a very large number. In the case of 14 billionths, the small KEQ, 14 billionths, we would need an extremely small number over a very large number in order to get that. This reaction favors reactants. And the reactants, if you remember, were calcium carbonates, which is what stalactites and stalagmites are made out of. So the reaction is favored. It takes a long time still for the reaction to make stalactites and stalagmites, but it's favored. Okay, quite a great deal. Now, large and small aren't very good descriptors. What do you mean by large? What do you mean by small? Is 10 small? Is 5 small? Is 0.05 small? Well, this is just a ratio of products to reactants. So what we're going to define as the thing to compare to is going to be 1. Okay, 1 is going to be neither large nor small. Okay, things that are larger than 1 are what we're talking about here. Things that are smaller than 1 are things that we're talking about here, because the way to get 1 is to have any number we like over any number. In this sort of reaction, nothing is favored. All right, nothing's favored because, yeah, I got the same number of reactants. I'm sorry, you've got the same number of reactants as you do products. All right, back to this. All right, so again, this is a very small KEQ. That suggests that this amount of stuff is small, whereas this is going to be large. And since the hydronium is on the same side as the calcium carbonate, it's also going to be making a large amount of calcium carbonate. So this is large on the product side. All right, how do we actually write a KEQ? Well, first we have to have a balanced equation. Then we write out the equilibrium expression. We place product concentrations in the numerator. We place reactant concentrations in the denominator. As I noted before, solids and liquids are left out of a KEQ expression unless it's a homogeneous reaction. If it's a homogeneous reaction, everything's solid, then you leave all solids in. If everything's liquid, you leave all liquids in. But heterogeneous reactions are what we do 90% of the time, and you always leave solids and liquids out of heterogeneous reactions. The final step is that you have to use the coefficients as exponents for each of the concentrations. What does that mean? Well, that means that if we had this reaction, which is the production of water, one possible production of water anyhow, I'm going to call these all gases. If we had this particular reaction, the way to construct a KEQ is going to be to write the products over the reactants. Products, water. There's only one product here, and it's going to be water. The reactants, there are two reactants, hydrogen and oxygen, both being gases, so I can write both of them, just like that. The final step, that third step, is this coefficient has to get written in as an exponent on water, so I'm going to put it right there like that. This coefficient also has to get written in, so we're going to put it right there. Notice oxygen has no coefficient. Actually, the coefficient is 1. If we put a 1 here, it's the same as not putting anything, because anything to the first power is itself. So we're just not going to bother with it. But this is basically how we come up with the KEQ expression. Again, to solve for a KEQ, to find out what this value actually is, we'd measure the concentration of water, we'd measure the concentration of hydrogen, and we'd measure the concentration of oxygen. All right, so continuing where we left off here, let's take the whiteboard away. All right, so that's basically how we write an equilibrium expression. KEQs, the whole reason why we're calculating KEQs is because we want to see if the reaction is favorable or not. More products are formed, what that's going to tell me is the numerator is larger. That means the KEQ is going to be larger than 1. We talked about that previously. We say that the conditions of this reaction favor the products, or sometimes we say we want to talk about the reaction. We say the reaction is favorable. Notice we can talk about it both ways. We can either talk about products being favored, or the entire reaction being favorable. The reason why the reaction is favorable is because why do you do a chemical reaction? Well, you want to make products, okay? If more reactants are formed, then the exact opposite is true. That means the denominator is larger, which means the KEQ is small, all right? We say that these conditions favor the reactants, or if we want to talk about the reaction itself, we want to talk about the reaction being unfavorable, because you want to make products, and you're not really making products. You're making lots of reactants. Some more visual examples, just to point out. KEQs that are relatively small, like this one. The book demonstrates that you can draw the arrow larger going backwards to represent the fact that you're making more reactants. And the pie graph here clearly shows that there's more reactants in this equilibrium reaction. Okay. What does a KEQ of 1 look like? Think about what the pie graph would look like. Yep, that's right. It's going to be half and half. A KEQ of 1 means that the products and the reactants are exactly equal, 1 over 1, or 20 over 20, or 2 billion over 2 billion. It doesn't matter. The KEQ is going to come out to be 1. Notice the arrows are exactly the same. And then the last example that I've got here is a relatively large KEQ. All right. Notice that, again, the arrowhead pointing towards what's being produced more of, products for a large KEQ. And notice here again, products is this light orange color, and that's definitely a product-favored reaction. All right, I think we're up to our final example here. We've got this particular chemical reaction. We should see if we can write a KEQ for it. You might want to press pause for a moment and actually write the KEQ. The KEQ turns out to be, we can't use the water in the KEQ, so we're going to put the product on top and the other reactant on the bottom. So it looks something like this. The bicarbonate ion and the hydronium ion and the H2CO3 right there. Okay. Now, this question down here is posed. It's very much similar to a lot of the technical questions I can ask you. It tells you that the H2CO3 compound has a molarity of 3.3 times 10 to the negative second. The concentration of the bicarbonate ion is equal to the hydronium ion concentration, and the hydronium ion concentration is 1.19 times 10 to the negative fourth. All right. So we're going to be asked to solve or determine what the KEQ is. All we have to do is plug these things in. All right. The bicarbonates and the hydronium ion concentration are given right here, so we're going to plug that in twice. 1.19 times 10 to the negative fourth times 1.19 times 10 to the negative fourth. And the H2CO3 is given as 3.3 times 10 to the negative second, so we put that on the bottom. This is where doing order of operations in your calculator is important. If you understand how to do it, you understand that this problem requires that you do what's on top first and then divide by what's on the bottom. Check it out on your calculator and make sure you get it right, because this is a typical problem that people will get wrong because they don't know how to use their calculator, because the calculator's dumb and doesn't understand order of operations. If you did it right, you got 4.29 times 10 to the negative 7. If you did it the most common way to get it wrong, you got 4.29, but you got times 10 to the negative 11. This means that you've got to probably pay attention to your, please excuse your dear Aunt Sally. Most of the time I think the problem is not having a parenthesis up on top around the whole thing. Okay, so make sure you didn't get that. All right. Here we go. The homework is to complete the KEQ worksheet. Like I said, we're looking at the evens. Okay, good luck.